Good evening, everyone. So I'll wait for just 1 or 2 minutes, then I'll start. Okay, so let's start. So in the previous class, I have discussed on the various linear algebraic problems where I have discussed unitary matrix, then Hermitian matrix, the properties of them. Then, very importantly, I have discussed about the diagonalization of a matrix. So, so there I have shown you how you diagonalize a matrix by forming a secular determinant, or you can find a unitary matrix which will diagonalize the matrix you want to diagonalize actually. Now, we have also seen that the diagonalization of a matrix can be done in two ways. So we have discussed both of them. So today, so why is that actually important, the diagonalization of a matrix? So in your course, you have seen that the Fock matrix that you form for first you form for a from a initial guess, then you keep repeating the process until it gets converge to a converged energy solution, right? So in that every step you form this Fock matrix, which was F mu nu, then you diagonalize this matrix to get diagonalize this matrix to get the eigenvalues and the eigenvectors. Now, unless or until this gets converged, the total energy, you keep repeating this process. So that's why I've discussed the diagonalization process. Now, I'll quickly show you a very brief Python code by which you can diagonalize a matrix, and then I will solve couple of the problems that I have promised in the previous lecture that I will solve, and I think in the previous lecture I have solved one problem variationally, and then I can connect I'll connect the two problems why they were giving the same eigenvalue. I'll come to that, then it will be even more clearer. Now, mm, let's see that how we can diagonalize a like using a code. So before that, so let me just briefly tell you. So let's say you have a matrix O, and that is in a different basis. And we have also discussed in the previous class how you can like you have a given set of basis I, and there is another set of basis alpha, and both are they are orthonormal. And how can you actually go from one basis to another basis by a unitary transformation that I have already shown. And then and let's say in one of these bases, this your O matrix is not diagonalized. Then I have shown you that by means of a unitary transformation, you can go to a representation where this omega is a representation of the O operator in a different basis, and where this is diagonalized. And I have also shown you that the column, so let's say your this omega is a n by n matrix, then your U is also a n by n matrix. So it's a n by n matrix, and each of these column, so this column 1, column 2, column 3, dot dot dot, they represent the eigenvector 1, eigenvector 2, eigenvector 3, and so on. That I have already shown you. Now I'll show you how to check this through a Python code, a very simple code. It will take just few minutes to show you. So let's go to, so you can open a Google, and there you can search um, Google Colab. So then we'll come to this page, and from where you can open the uh, any new Colab file. So that I have already opened here. So you can do this. Now let's see how we are going to code this. So this is not required to know Python and all. I'm just showing you for a demonstration purpose that actually how it is done. Because again, I'm mentioning that in your Hartree-Fock code, you actually form the Fock matrix in the given basis. So F mu nu, and actually you have to diagonalize that F mu nu to get the eigenvalues and eigenvectors. And essentially there, it's nothing but the diagonalization of the Fock matrix. It's not has to be in this way. There are many other method possible that, but this is one of the way that you can diagonalize a matrix. And most of the codes actually use this kind of thing. So NumPy is a Python library. So we'll import this by import statement NumPy as np. And let's run it. So it's allocating time connecting to Python 3 when it's connected. So yes, so it has run. So now let's form a matrix. I'm giving you a name A. So it's a variable, and so I'll convert it to a matrix. So this is a list, blank list, and inside this list, we are creating another list. So let me take the example 2, comma 1, comma 0, and then another item 1, comma 2, comma 0, and then sorry, this will be again in list. Yes. So then again another list items. Let's say 0, 0, and 3. So now you can see this matrix is basically a Hermitian matrix, because we actually deal with the Hermitian matrices. So I have defined here is a Hermitian matrix. Basically, it's a symmetric matrix because I'm not dealing with the complex number. You can see that this 1 2 element, that is 1, and the 2 1 elements, they are same. Even this is your 1 3 elements, and this is 3 1 elements, and they are same. So basically I have taken a symmetric matrix here. So now this is your matrix. So now we have to do it. So we'll define our O matrix as np dot as array, and you pass this matrix. Right. So let's print matrix print. Oh, let's check that this is not giving any error. Yes, so it's giving us a matrix. Now, how you can diagonalize it? So let's write here. So, so we have defined that the eigenvalues as omega and the coefficients or the eigenvectors as u. So we'll stick to that. So omega and u. So these are two variables. This is numpy dot lin linear algebra, and so these are the class method that is already defined there, so you have to just fetch it out correctly. So I can use EIGH. This is for to diagonalize a Hermitian matrix, and for any general matrix you can use the EIG. So I'll use the EIG, but as I can see this is a Hermitian matrix, I can also use that EIGH also. So let's use EIG, and you pass the matrix you want to diagonalize. Okay, so it's done. Then let's print uh, eigenvalues, eigenvalues. So whoever knows Python, that is very trivial to them, but I hope that many of you don't know it, and certainly again I'm clarifying that you don't have to know it because this course doesn't seek for any coding, but just for demonstration purpose, I wanted to show you how it's done. So this is eigenvalues, and let's print the eigenvectors also. Eigenvectors, so they are actually combined. So the eigenvectors are combined. Print the U. Okay. So before that, so let's go back to how we're going to solve this. Okay, and let's see whether uh, this is giving you the correct result or not. So the matrix you have defined O as 2, 1, 0. Then you have 1, 2, 0, and 0, 0. So the so we have already discussed how to solve this kind of matrix diagonalization. So you have to basically form the secular determinant. So you have to do a minus 1 lambda. So basically what you do, so you have OC is equal to lambda C, right? So you can do 1 lambda then unit vector times C is equal to uh, is basically 0. So you have to take the determinant O minus lambda I is equal to 0, then you will get the solution. So that's what I'm basically doing here. So you have 1 0 1 2 minus lambda 0 0 0 3 minus lambda. So this is your determinant, and let's put it is equal to 0. So I will expand this in this row because the two elements are 0 here, so I have to calculate this 3 minus lambda. So otherwise, you could have done in this row or in this row, but I think this is the best way you can do it. So 0 times and 0 times they will both vanish. So only term that will left 3 minus lambda, and then you have 2 minus lambda 1 1 2 minus lambda, right, is equal to 0. And this is giving you 3 minus lambda and 2 minus lambda square minus 1 is equal to 0, and this will give you, so one of the solution is definitely your 3 minus lambda, 3 minus lambda is equal to 0, and this will give you lambda is equal to 3. This is one of the solution, and next you have 2 minus lambda square minus 1. We have 2 minus lambda square minus 1 is equal to 0. So you can 4 minus lambda square, and now you have 4 lambda minus 1 is equal to 0, right? So you have lambda square, sorry, this is lambda square, you have lambda square, then you have 4 lambda minus 3 is equal to 0. So I'm just showing you because so you can take lambda common here. So lambda minus lambda square, 3 lambda minus lambda plus 3 is equal to 0. So take lambda common, lambda minus 3 minus 1, lambda minus 3. So you have two other solutions, lambda is equal to 3 and lambda is equal to 1, right? And in the previous, you also got lambda is equal to 3. So as this was a 3 by 3 matrix, you got 2, 3 solution. So this 2 is degenerate, okay, and this is another eigenvalue. Now you put back this lambda here, and you can get this corresponding C. That I'm not going to show here, but I have just shown you that this is. So I expect these 3 eigenvalues from there. Okay, so let's see. So this is our matrix. So we have, this is the main diagonalization step. So this is the main diagonalization step. So if you put a hash in Python, this is basically is a command out statement. So it doesn't read that the line from there. So let's run it. See, this is your matrix, and this is the eigenvalues. 3, 1, 3, and the eigenvectors. So this is your U matrix, right? So this is the first row, this is the second column, and the third column. They are actually the eigenvectors. And let's verify. So what I expect, um, so so the thing is, let's first check that with this U vector, unitary vector, can I make the, so certainly this A matrix is not diagonalized. So from this rule, if you remember this, so if I perform this U dagger, O U dagger, so this matrix has to be diagonalized. That's what we have learned. So let's do this first. So let's print unitary transformation of O matrix, right? So print. So how do you write O dagger here? So if your matrix is U, so you have to. So if you remember that the adjoint of any matrix is basically you have to take the transpose, then you have to take the uh, corresponding conjugate or complex conjugate of that. So here our matrix is real, so taking conjugate doesn't actually give you anything, but anyway we'll do it. So how we'll do it, how you do it, u dot t, you take the transpose, then you take the conjugate. So now this u dot t dot conj is actually your u dagger, okay, and this is the matrix multiplication, how you do it. So this at the rate sign, then you put the O in between this and the U matrix. So O is sandwiched between this U dagger and U. So I expect this now it to be diagonal. See this matrix. Now your O matrix is diagonal, and the eigenvalue 3, 1, 3 is basically the eigenvalues from here. So this is one check. Now the another check is U dagger. So U is a unitary matrix. So U dagger U has to be a identity matrix, right? So you will get basically 1 0 0 0 1 0 0 0 1. That's what you should get. So let's print check unitary print. So u dot t dot const. So this is your u dagger, and so there are many ways you can do this matrix multiplication. So I'm using this at the rate. You can use np dot dot. You can use matmul. You can use einsam. There are various way you can do this, but for this simplicity purpose, we are using this at the rate. So u dot t. So you have taken u dagger, and now take the u. So I expect this to be, and see, this is the unitary 100 0 1 0 0 0. So yes, this is unitary, and this confirms that the the columns are actually orthonormal, right? Because we knew that for a Hermitian matrix, the eigenvectors has to be orthonormal, and as this is a unitary matrix, that the column. So if you want to see that, if you take a single column, and so you can actually show this that. So should I show this? Okay, let's do this. So actually, this is your eigenvector, right? And the first column is corresponds to your first vector, eigenvector. Second is the your second eigenvector, and third is the eigenvector. So let's print. Um, so first, so let's do in this way. Let's define two variable I is equal to 0. So Python numbering starts from 0. So 0 means the first column. I can do that. And let's say j is 1, the second one. So so we can do that. So what we are going to do is that to show you that the eigenvectors are actually orthonormal. So for that, what we have to do, um, so we have to fetch out the each of these column. So how we'll do it actually? Um, let's say that ith column is basically, so your u vector, and you have to fetch the ith column. So this means you will take all the row elements which belongs to this ith, that is we have put as 0. This is 0th element, and your jth column is similarly this, right? Let's print ith column and jth column. Okay, I and jth column. Let's print this. So so see, so now actually they are giving you back a one of the this in a form of row, so we can actually resave it. So that's not an issue. But so see that the zeroth means your first column, right? So which is 0.070, and this, and that is actually printed. So I'll just I'll put a dot transpose here, which will actually make it a column vector. So that will be, I think, ith column and jth column. Actually, I can reshape it. I can reshape it to uh, -1 1, which will, I think, make it column vector. Yes, so now it has made it a column vector. Now let's perform the uh, multiplication that we are talking about actually. So we can do print orthonormal to normal or not. We'll check that. So here I and j are different. So I expect that it will come out to be 0. Let's print ith column. I can take dot conj and dot transpose because I have to take dagger and dot transpose dot can dot transpose dot conj. It doesn't matter, but and the red is j column. J column. This is not anyway required. I can anyway remove this. It's giving you 0. Now, if I put I and j to be 1, so they should be normalized, and it's giving you 0.999, which is actually very close to 1. So they are orthonormal. So now you can also see that one problem that we are facing actually back then. Um, so so what was that? So that was basically if you write it in this way. So so O OU basically we're writing it in this format. OU basically uh, U omega. So if you switch this, you will actually not get the thing, right? So let's see whether this you can see from here itself. So print U. So O is operating on U vector and print your U omega, right? So print. So what do you want? O matrix multiplication with U. And here we want print U matrix multi. So one thing to note that this omega they have given you in a form of a list, right? So this is a one-dimensional thing, but to have this matrix multiplication, you have to make this omega in a diagonal form. So what you can actually do is that you can define a uh, omega diagonal where you can diagonalize this. So you can make the list as a diagonal elements. So I'll show you how does this look. Then maybe it will be clearer. So print omega diag. I'll show you then. So omega underscore diag, right? So see these W diag or omega diag, actually what we have done is these eigenvalues we have, so this is a 3 eigenvalues, right? So what we have made is that if your O matrix were a diagonal, so we actually would have get this, right? Would have gotten this one. So we have made these 3 list of elements to a matrix elements like this. So this you can do with this np.diag function. So I'll just remove this. So what we expect is that print U omega should be as similar to this your OU. So Let's print this and check. Print. So what we want? U times omega di. Now see, your OU and U omega, they are same. And what actually it did, so if you see, this is your first eigenvector. This is actually scaled by the your first eigenvalue. So lambda times your eigenvector. So this is the 3 times of that. And again, this is the one times. So it is just the same. And this is also 3 times. So this is actually you are getting an eigenvalue equation. And U omega, they are same. Now if you do the reverse one, you will see that they are not the same. So let's also check here. See, they are not the same. So they are scaling in a different way. So here it is 2, 1, 2, 1, and in the row it's actually coming in this way. So it is actually scaling in a different way, this vector, which we have discussed in the previous class itself. So the right way to do is actually the previous one. Yes, this one. Okay, so we'll not go into this. So you can play with this matrix. You can put any matrix there, and you can check that whether you are getting this stuff or not. So I'll encourage you to play around these things. Okay, so having discussed this part, do anyone has any question?
Unknown.
Okay. Are you familiar with Python or any programming language?
Yeah, but actually I joined a bit late, so
Okay, okay.
I could
So
not follow everything. I'll watch the recordings.
okay, okay. That sounds good. Okay, so having done that, let's solve the problem that we have discussed back then. So, so I'll solve the problem, then I'll try to connect to that lecture that why we are getting that eigenvalue. So, so the problem goes like this. You are given a matrix O, which is a symmetric matrix O11, O12. So symmetric matrix means there's off diagonal elements there. Sorry, that uh, OMN is equal to ONM. This is definition of a symmetric matrix. So we're taking this as 2, 2. So now this matrix is not diagonal, like a diagonal. So can we, so that means this, your O12 is not equal to 0. So that's why it's not diagonal. So can we make the diagonal? So yes, we have the procedure by which we form the secular matrix and you solve the equation. Now, can we solve this equation by means of U dagger O U? So can we find out this U so that we can make this diagonal? So we'll do in this way. So, so the thing is, you have to get this O U matrix multiplication, right? So let's assume your U is U11, U12, U21, and U22. We don't know the elements, so we have to find out this matrix multiplication. So let's first do with OU, which is basically O11, O12, O12, O22 times U11, U12, U21, U22. So now if you do the matrix multiplication, you will see this is basically O11, O11 U11, right? O11 U11 plus O12 U21, and now for this 1 2 element, this is O11 U12 and O12 U22. This for the 2 1 element, this is O12 U11 O22 U21, and you have, so uh, so we can do this, but let's do in different way. So not calculating this, instead eventually we have to calculate this. So but first let's define how my U matrix or unitary matrix is going to look like. So eventually we have to calculate this U dagger OU. So but before that, if so we have to find out that the matrix element of U, how does it look like. So the criteria of this transformation is that this U matrix is a unitary matrix. So that means it has to be a identity matrix. So our U has to be a identity matrix. So what is your U dagger U? So how do you write the U dagger? U dagger means U transpose and then conjugate. So U11, this will be U21, and this is U12, and this is U22. So you take the U dagger U, which is U11, U21, U12, U22, U11, U2, U21, U22. So it will result you a 2 by 2 matrix, because this is a 2 by 2 matrix, this is a 2 by 2 matrix, and it will give you a 2 by 2 matrix, which is U11 square, U11 square, U21, U21, right? Or we should write actually U11, U11, because we don't know that whether this U11 or U21 they are complex or real, right? So it's better to write them explicitly, U21, U21, or here it will be U11, U12 plus U21, U22. So here it will be U12, U11, U22, U21, 212, U22, 21. At last you have U12, U12, U22, U22. So we have two condition here. So that so the condition is that this U11 and U11 and this item has to be 1, and another thing is that this off diagonal element has to be 0. So how can we get this? So let's say, so here I'll show, if your U matrix looks like this, let's say cos theta, sin theta, and sin theta minus cos theta, then you can easily see that if you take the U dagger U, if you take the U dagger U, so what you actually get is that cos square theta plus sin square theta 0. So I'll show. So U dagger U is basically cos theta, sin theta, and sin theta minus cos theta, sin theta minus cos theta. And here you have cos theta, sin theta, sin theta minus cos theta. So now you do the matrix multiplication. It will be cos square theta plus sin square theta, and in here it will be cos theta sin theta minus cos theta sin theta. And here it will be sin theta cos theta sin theta cos theta minus sin theta cos theta. And here it will be sin square theta plus cos square theta. So for any value of theta, your sin square theta plus cos square theta, they are 1. So you actually get the 1, 0, 0, 1, which is the identity matrix. So if you define your unitary matrix in this way, so this criteria is getting fulfilled. So U dagger is equal to 1. So now you can perform this U dagger OU operation. So which we are going to do actually. So O is O11, O12, O12, and now you have O22. And what was U? It was cos theta sin theta minus cos theta, cos theta sin theta, sin theta minus cos theta. So let's do the matrix multiplication. So this will be O11 cos theta plus O12 sin theta. Then you have O11 sin theta minus O12 cos theta. And here you have O12 cos theta plus O22 sin theta, O12 sin theta minus O22 cos theta. Then again you have to multiply this with U dagger. So what is our U dagger? U dagger is cos theta sin theta. Actually they are same. Cos theta sin theta and sin theta minus cos theta. So now let's do this. This will be O11 cos square theta, and you have O12 sin theta cos theta. Then you have, so this item times this and this times this. We have O12 sin theta cos theta theta sin theta O22 times theta. Right. Now you have, now you have to multiply this with theta sin theta cos sin theta O11 sin theta cos theta minus O12 cos square theta and then it will be in the second column. Correct. That should 1 cos square theta 1 2 theta. mm, and then one, theta, one, and oh, the raw matrix multiplication. So this is sorry for this. This will be cos square theta over 1 to sin theta. Then uh, then again there will be other terms that I missed. So it will be sin theta. So 1 sin theta cos theta plus 2 sin square theta. Yes. So 2 sin square theta 2 sin theta. Right. Is cos theta sin theta cos theta, and sin theta sin theta cos theta. Can you check where I'm getting wrong? Uh, so if you O and U, so this is giving you O11 cos theta plus O12 sin theta, and then to the oh, so then you have to multiply this sin theta with this. So this is O12 sin theta cos theta. I just got lost. So this is O22 sin square theta. So if I write down all the other terms, it will be something like half O11 minus O22 sin 2 theta. So you can actually take this is actually O12. So sin theta cos theta. So this is basically 2 O12 sin theta cos theta and 2 sin theta cos theta. You know that is actually sin 2 theta. So I'll just write down the final form. Otherwise, everything was correct. So it's taking some time. So I'll just write the final result, that is O11 cos square theta plus O22 sin square theta plus O12 sin 2 theta. This is your first term, that is O11. Sorry, the first 1 matrix element. Then your off diagonal term is half O11 minus O22 sin 2 theta minus O12 cos 2 theta, and the other terms are half O11 O22 sin 2 theta minus O12 cos 2 theta, and the last diagonal term O11 sin square theta plus O22 cos square theta minus O12 sin 2 theta. Now this is your U dagger OU. So to make it diagonal, so what is will be the criteria? The criteria should be this off diagonal term, this term, and this term has to go zero, right? So now if we put some condition that it is going to zero for certain theta, let's say theta zero, then we'll get the theta and theta 0. And now if we put back this theta 0 here, this cos theta 0 and sin theta 0, that will be your eigenvectors. And so this will be two eigenvectors, and you will get actually, now when you put this theta 0 here and here, you will get the eigen value. So that's what we are actually going to do. So now let's take the first eigen vector, so or the diagonal of diagonal elements, that is your half O11 minus O22 sine 2 theta minus O12 cos 2 theta is equal to 0. So this term we are putting it to be equal to 0 for a certain value of theta. So now if we solve it, we have O12 or half O11 O22 sine 2 theta is equal to O12 cos 2 theta. Now we can take this half over there, so it will be 2. Now we can take this sine 2 theta by cos 2 theta here, and you can take this parenthesis term here over here, O11 minus O22. So now we have tan 2 theta is equal to 212 O11 O22. Now if you solve this, you have theta 0 is half tan inverse 212 O11 minus O2. Right. So for this theta value, if we have the matrix elements, right? O12. So this is the matrix that we wanted to diagonalize. O11, O12, O12, O22. So we know the matrix elements. Now, if we put this matrix elements here, we'll get the certain theta 0 value for which this U dagger OU will be diagonal. So now if you put this theta 0 back here, so it will be 0, right? Because this is the condition that we have solved here. So for this, you will get the diagonal matrix. And so if you put the theta 0 back here, you will get the first eigenvalue and you will get the second eigenvalue. And how does your U matrix will look like? It will be cos theta 0, sin theta 0, and it is sin theta 0, cos theta 0. Right, this is your first eigenvector. This is your second. This is our second eigenvector. That's what we have discussed in the previous class. And so now my omega 1 and omega 2. So there is nothing actually. So you have to just put that theta is equal to theta 0, and you will get the omega 1 and omega 2. So now if you remember in the very previous class of ours, so remember this form, theta 0 is equal to half tan inverse 212 O11 minus O12, right? Now, if we go to our previous class, I think that was in the week 2, where, yes, so we had this matrix and see the form of this coefficient or the vector C. This is basically cos theta and sin theta. And when we solve this, we got this theta is equal to half tan inverse, the same thing that we have got here. So now what's the catch here? You look at this vector cos theta is equal to sin theta, right? So now this cos theta sin theta is basically one of the eigenvector of your the the O matrix. So this matrix, for this O matrix, so so for this matrix that you have diagonalized, one of the eigenvector is basically your cos theta and sin theta 0. So, so there we got the exact eigenvalue. So variational theorem says that your your eigenvalue, if you solve variationally, so then you can, so if you start with a trial function and you keep varying the parameter, so unless or until you get the minimum, so there you can say that your eigenvalue is basically the greater than or equal to the exact one. So we got the exact one because we started with the exact eigenvector, and that is the cos theta sin theta. So that's why we got this solution. So that was the thing that I wanted to mention, that if you put the eigenvectors in the column wise, then you actually get the eigenvectors. So so this is your unitary matrix, all about unitary matrix transformation. Now, in the rest of the class, what I'll do is that I'll revisit the Hartree-Fock problem. So these are the very great slides from I have taken from Professor David Cyril. He's very famous for electronic structure theory. So I'll discuss. So for this Hartree-Fock, most of the things you know, but I'll again revisit all the things from his slide. Then there will be certain terms will be advanced, so those I will not discuss here. And in the coming lectures also, I will solve. I'll show you his slides and his notes, and those are very important, or those are very detailed in nature. So and in the next class also, what I'm planning is to do is that in detail I'll discuss the Koopman's theorem, where I'll prove that you can actually get the ionization potential or electron affinity is a rough estimate from the orbital energies that I'll prove. So even if I have the time today, I can also solve it. So let's go through one by one slide. Uh, so what is Hartree-Fock for? So we actually don't know the uh, exact eigenvector for the Hamiltonian, the multi-electron system that we are dealing with. So this is basically a electronic Schrodinger equation, right? So uh, yes. So the thing is that we actually don't know that the what is the exact solution of this electronic Hamiltonian. So anyway, we have to get a good approximation for this, right? So we want to solve this this Schrodinger equation. Now, what is this R semicolon R means? That means we are actually in the Born Oppenheimer picture. So where we have fixed the nuclear coordinates, and then we are actually solving the electronic degrees of freedom. So we are actually separating out the electronic degrees and nuclear degrees of freedom. So we are basically in the Born-Oppenheimer region. So that's what is it mean. This electronic energy is a function of this R. So if you vary the R, you actually what you get is that potential energy surface that I will discuss in the next slide. So this gives us the electronic wave function. So now if you have the electronic wave function, you can calculate various properties like dipole moment, polarizability, and other properties. So actually what you do from the wave function, you can calculate the density, and from the densities you can calculate the dipole moment and polarizability. But in this course actually we basically talk about energies, and these are very advanced things. There's the calculation of property, so I'll not discuss these things. So but if you have the wave function, you can calculate the dipole moment and polarizability and other stuffs also. So now the electronic energy is the potential energy surface. So that means the electron energy is a function of your nuclear coordinates. So let's say if this is your nuclear coordinates, so now at a certain value of R, you got the electronic energy this, right? Now you change the R, you got another energy. Now you change the R like this. so you can get a surface like this. Now if you join all the points, then you can get a potential energy curve of surface. So if you vary the nuclear degrees of coordinate, right? Now the Slater determinant, this is already discussed. So the John Slater actually introduced this Slater determinant. So here, so what in this column, actually they have fixed the orbitals and they have varied the electronic um, electronic positions or electronic, I'd rather say this is the combined coordinates of electron 1, where they have all the space coordinates as well as the spin coordinates as well, right? And so here also the second orbital and so on, you all know this, and this is the shorthand notation that how you denote the Slater determinant. So you will assume that the electronic wave function can be written as a single Slater determinant. Now the Slater determinants came into the picture because we need the antisymmetric wave function, because we are dealing with the fermionic system, right? So and the Hartree-Fock. So when we will solve the Hartree-Fock equation, that will give us the orbitals that we are interested in.
Can you like once again, it was done, but like how the normalization constant can be calculated?
So this 1 by root over of n factorial.
Yeah.
So okay, so that you can actually you can do a practice with a two electronic system. So you actually take a chi1 and chi1, or let's say chi2, right? And let's put 1 2 here and 1 2 here. Okay, and you don't know the normalization constant, and you put in here, and then you then calculate the determinant, that is your chi1 1, chi2 2 minus chi2 1, chi1 2, right? So now if you do this, so the thing is you have to get your psi star psi is equal to 1. Now if you do this, that eventually you will get 1 by 2 for the second determinant, and you practice for the third determinant itself. There you will see that to get this, so for
Oh,
from
okay,
this,
got it.
okay, from
Mm.
there you can actually get this n factorial terms here. So actually you will see when you have a two orbital, you have actually two terms, right? Two factorial terms. Now when you have a three determinant, so you actually have six combination of the, so three electrons. So they are actually there in the three orbitals, and you have six terms, and to normalize the six terms, that 1 by root over of 6 term will come, and there you can see that 1 by root over 6, then when you do the psi star psi, it actually gives you 1. You can do the simple practice with this. Now, Hartree-Fock molecular orbital. So here they have sketched that how we'll solve the Hartree-Fock molecular orbital. So for atoms, so they are actually talking about the molecular picture. So invoke the Born-Oppenheimer approximation. That means you fix the geometry of the system that you have interested in, and on that geometry you perform the electronic structure calculation. So express the electronic wave function as a single Slater determinant. Okay, so here we are doing the approximation here. So we are telling that the electronic wave function is a single Slater determinant, and which is not. We know that. Now solve for those orbitals which minimize the electronic energy by the variation principle. So we have defined the Lagrangian, and we solve this dl with respect to chi, as well as dl with respect to that Lagrangian parameter, right? And we solve it, and we actually get the lowest energy solution. This winds up being mathematically equivalent to assuming each electron interacts only with the average charge cloud of other electrons. So you have seen in the Fock operator, so there is a summation over second electrons, that is all the orbitals present. So this is basically interaction of one electron that is present there with the overall average cloud, charge cloud. Now the operators. This is Hi, this is the core operators. This actually has the kinetic energy of the ith electron and the interaction of the ith electron with all the nucleus. So the sum goes over A. So this is the one electron operator for electron I, its kinetic energy and its attraction to all nuclei. And now this is your 1 by Rij term. So actually they are in the atomic unit. So H cross and mass of electron, they are all saying that they are equal to 1. So that's why it is 1 by Rij. And this is a two electron operator, and this represent their Coulomb repulsion, that between I and J electron. So this is the repulsion term that we have, and this is the full electron, the summation of your one electronic operation and the summation of the so careful that this is a I less than j. That means that we are not double counting the interaction between two electrons, and this is the VNN. This is basically the nuclear repulsion energy. Now, if the variational theorem says to minimize the energy, what is the energy of a Slater determinant? So now for this Slater determinant, we have discussed the Slater rules. So there we can actually get the Slater determinant. So here you see very carefully that E electron is a function of R that I have already discussed. And this is a bracket notation. And now you see the integration over which. So the integration is over the all the electronic coordinates. So now if you integrate out, you actually get a number. So then there is no variable left. Okay. So now how to get the matrix element? You take the Slater rules and you calculate the matrix element. So now then we got that E Hartree-Fock is basically the summation of IHI, where I goes from 1 to n, the number of electron, and then you have this IIJJ. So I'll just mention here, Professor Cyril has taken the Koopman's notation, or the Koopman notation, or the chemist way of representing the two electron integers. Just a second. So Koopman's way of doing thing is that if you have a IJ KL, that means the first electron in ith orbital, and this is J1 star. If you actually take the integration, and then you have K2 or K star 2 L2, and you take d tau 1 over all two electronic integral. So now the same representation in the, so this is your 1 1 2 2 notation that we actually call it. So you have to write it in the Dirac notation, actually 1 2 1 2. So in the left hand side you have IK, or sorry, IK and JL. So this so this is actually, I should not put star here, because when you write in the bra form, that is actually star, but for your understanding purpose, this is actually star, this is star. So that's how you write it. So he has written in this form, the Koopman's form. Okay. So this is your 1 1 or 2 2, and this is the exchange term, and this is the Coulomb term. So now see, this is they have written that one electron integral, that is your H core matrix element, H IJ matrix element, which is chi
Uh,
I star. Yes.
why is it necessary to write it like this? Is it any is does it provide any benefit? The Koopman's notation.
So the chemist actually basically write in the Koopman notation. That's why it is called a chem. So there is, both are same. Like you are just different notation for writing a certain integral. There is no benefit over it. So there are just two notation available in the literature, but the modern theoretical chemist actually follows the physicist notation, like uh, like the bracket
Okay.
notation. But there are very certain previous papers there actually they mention this Koopman notation. There is nothing gain or nothing benefit about this notation. They're actually different way of representing stuff. So now you see the one electron integers, they are saying this is a four-dimensional thing. Now why it's four-dimensional? The four-dimensionality is coming from actually your to represent this integral. Um, so this I is depending on the space part, that is the xyj part, and the spin part, right? So if I tell that the overall the xy part as a single coordinate and the spin part is a other coordinate, so that is hidden inside here x1 and x1, right? Then this is a four-dimensional because this j can be other integral also. And for this eight-dimensional thing, actually this ij and kl, there are four terms, that's why it's a eight-dimensional thing. Right, now let's go to the physical meaning of the terms. You already know this stuff. So each electron contributes a one electron integral. This chi star x1, this hr1, and this is a matrix element.
Can you again once again go over the like four-dimensional term? Why is it?
Okay, so the four-dimensional term is because your I, so this actually a so so this x1 is basically a combination of your space integrals and the spin integrals, right? So actually x1 is basically your r1, and let's say it can be alpha or beta, and the xj or the second orbital, the electron is there, so that is also a r1 and alpha or beta, it can be anyway. So in that way, that this one electron integral, they're representing as a four-dimensional thing. And for the two electron integral, so if you see the ij and kl, so there,
Hmm.
yeah, so there is one space coordinate for the I and the spin coordinate for I also, and for j also there is spin coordinate and space coordinate. So summing
It
up all the, you have eight-dimensional thing.
it comes from the number of coordinates each
Yes, yes. So if you
function
consider
depends
the,
on.
yes, the total space integral to be one-dimensional, actually, so actually that is a four-dimensional thing. So this x1 is basically a four-dimensional thing. X, y, z and your spin.
Actually, in the classes there was a like symmetry thing also, four-fold symmetry, eightfold symmetry.
Yes, yes,
So
that is a symmetry of your matrix. So if the orbitals are real, I think Professor Pal has discussed that very well. So that is a different thing. Four-fold symmetry and eightfold symmetry. Okay, now um, this looks like the expectation value of the operator H for an electron in the orbital X, so long as the orbital is normalized. Now recall that the H contains the electronic kinetic energy and the potential attraction and sum of all orbitals to get the total kinetic energy and interaction to the nuclei. So that is the actually meaning of this typical term. Now again, this term you know it very well. So this first electron, that is x1 electron, or this is actually sitting in the xith orbital, and another electron that is in xj orbital, and this is a density, right? Psi x star, chi I star, and chi I. This is a density. Probability of electron in orbital I is located at x1. So why I'm discussing all this? Because certain things is explicitly mentioned, and it will be very clear to you if you look at his slides. Now, this tells that probability of electron 2, that is x2, in orbital j here and located as x2, right? Now there is a two summation. You integrate over all possible location of electrons. So now what you are getting a Coulomb repulsion between electron at x1 and electron at x2 because of this 1 by r12. So overall, this integral represents the Coulomb repulsion between electron 1 in orbital I and electron 2 in orbital j. Now again, there is no physical meaning to exchange part. That's what he mentioned here. No direct physical meaning, consequence of the Slater determinant. So, or you can say the Slater determinants coming from the antisymmetrization, and because of the antisymmetrization, this is the exchange. That is a totally quantum mechanical term. There is nothing you can relate to the physical thing. Now, the Hartree-Fock energy example. So, so here the important thing is that I goes over J, so there is a no half term here. So because you are not double counting any interaction, so this is a simple example of the helium atom. So the helium atom is basically we write in a very colloquial term as one s2. So you have two electrons, one as alpha and one as beta, and the Hartree-Fock energy he has written in this form 1h1, 2h2. This is the kinetic and interaction energy of electron, and this is the kinetic and interaction energy, the nuclear interaction energy with the second electron, or the electron is sitting at the second or one is beta orbital, and then you have this Coulomb term and the exchange term. Now, the last integral is zero, and you all know it why, and but again I'll discuss 3 slides. Now, why it's zero? Spin factorization and the spatial orbital. Recall each spin orbital that I have just mentioned is a function of 4 coordinates. So you have spatial xyj coordinate and omega, that is a spin coordinate. So, and that is your spin orbital. And I have mentioned the spin orbital is actually a tensor product of your spatial orbital and the spin part. So I'll not go like why it's a tensor product, not a normal product. But yes, that's a different thing. So we normally write each spatial orbital as a product of a spatial part phi r and a spin part, which we might call as sigma omega. And actually, there is two thing like this, that is alpha and beta. And the operators in Hartree-Fock theory H and 1 by R12 do not depend on the spin coordinate. That is obvious because in H you have the electronic spatial coordinates, that p square by 2m term. So there is no spin part there, and 1 by R12. But again, this is totally is discussed in the non-relativistic framework. So when you go to the relativistic framework, so I'm just mentioning for your knowledge purpose. So when you go to the relativistic Hamiltonian or the Dirac Hamiltonian, the spin part comes automatically. And there, when you'll study the relativistic chemistry, so in the second lecture, I have talked about the Pauli spin matrices. They will like normally or naturally come into the mathematical picture of the Dirac equation. So this is totally is getting discussed in the non-relativistic framework. So that means that your H or 1 by R12 does not depend on the spin coordinate. That means an integral over x. So whatever the integral you are seeing here, right, you can actually separate out the spin coordinate. So that is what is basically done here. So we are writing this chi I as phi I r and sigma I omega, and similarly this chi j as phi j and sigma j. And see, there is two integration dr d omega. And now you can, so what does this sentence mean? That you can actually separate out this fellow because this depends on omega and this integration is over r. So you can actually separate it out. Now you have this spatial thing and this spin thing separated here. Now we can factorize the two electron integral, the exchange integral and the Coulomb integral in the similar fashion. So actually this is your ijkl. So starting from here, so this is the, so you can see that this is the space part and there is two spin part according to this ij and kl. And so usually this is alpha spin or beta spin, and we have also shown in that second class that this alpha spin and beta spin, that 1 0 and 0 1, how did they come and why they are orthonormal, because I'll again mention they are the eigenvectors of the S square or SZ operator, which is Hermitian. And from the postulate of quantum mechanics, you know that any eigenvectors of an Hermitian matrix are orthonormal to each other, and that's why this relation. Okay, so this is done. So now you can write this spin integration. This is the your one electron integral. So IAJ, and this is the spatial coordinate separated. So this integral only survives only the spin of the I or jth electron, or the electron that is there, they have the same spin. Then only it will survive, otherwise it is zero. So the one electron integrals survive if both spin orbitals have the same spin. Now what about the two electron integrals? So again, the two electron integrals survive if spins of ij, that is the your in the Mulliken's notation, ij match on the left and spin scale match on the right. Now we just did the generic one and two electron integrals, the ones in the Hartree-Fock. How do these repeats affect spin integration? So now this is very simple. This is done in the lectures also. Uh, so for these slides, whatever there in these slides, most of the things, I'll say 98%, 99% things are being covered. But again, I'm just showing you these slides. So in the coming lectures, I'll show you the basis sets, or maybe the configuration interaction singles, or in the later course, if time permits, or if I have the time, I can also discuss the details of couple cluster theory if I have the time. Or I have a question like, would you like to see a Hartree-Fock? So that will be very advanced thing to do, but I don't know whether I should do it or not. I'm just taking your opinion. That would you like to see how to write a Hartree-Fock code in Python, like starting from the initial guess to the iteration,
Yeah,
and
yeah.
so have you done that by yourself?
No, actually, no.
Okay, so I think that will be, but that may take another, let's say, one or two class. So, but
Okay.
it would be very interesting to do the full Hartree-Fock code. Actually, there is a GitHub repository that actually does this thing, but we can actually go along. So, as you are interested, so I think I should give it a try. So let's see how it goes.
So
Then I
can we write it in Python? Because I have heard like generally quantum chemistry programs, people use lower level languages. So.
Yes, actually, if you go so for the test purpose or learning purposes, Python would be great. So if you see the PySCF, the giant software that is actually written in Python. So, but you are right. If you go to the lower language like C++ or Fortran, the code will be much faster. But writing codes in Fortran or C++ is much difficult. So,
Oh yeah.
for a production level software, yes, you have to use the uh, lower level language. But nowadays, Python is very fast. So there are many modules like. I should not mention, but Numba, or actually, if you use the NumPy in the backend, NumPy it actually uses the C++ or C. So that's why it's very fast. But yeah, for the demonstration purpose, I think it's the best idea to write in Python. So
Okay.
I can show you. So maybe in the coming classes, I would like to show that also.
So the from the coming classes also you will be taking the summarizing the lectures content also, right?
Okay, if you want, so I can, yes, I can do that. But I think the lecture is very well discussed. I
Yeah,
thought that there will be. So if you have any problem, you can let me know. So as you were saying that you have some problem regarding Koopman's
yeah,
theory in the back then. So I can anyway discuss this. So what I was thinking that the Koopman's was not discussed in full detail, or I think the derivation part,
yeah.
so that I can do in the next class, and maybe
Mm.
that day, or even if you want, you can ask now also. So what was the doubt regarding the Koopman theory?
Basically, derivation like the ionization potential and electron affinity.
Oh, so were you being so
He
actually what
asked
you
to do it ourselves, but
so
I
yes, so actually I think he has asked to calculate the En minus one and
minus
E.
E n k. So
Yes,
minus E
yes.
n minus one HF. Yeah.
Sorry,
Yes.
this is zero.
Yeah.
So if you do that, actually you will get this minus.
Minus E.
So have you done that?
No, I tried to look into the book, but I got confused.
Yes, yes. So there is a very interesting discussion that can be done on this Koopman's theory. So actually, so what I have planned in the next class, I'll do this proof for IP, and
Mm,
EA will be generalized, and there are certain exercise that I can also discuss.
mm,
So in the next class, I'll address this problem. I'll explicitly show how is this done. Okay.
mm,
Okay. So this is the spin integration, and this is very simple. Um, so only this term will survive, and this is your Coulomb term, right? And the Coulomb term is integral always survives the spin integration because your 1122 stuff. Uh, so because of this stuff, your sigma I star and sigma, because they are the same, so they will always be one. So that's why Coulomb terms always survive. So that's why in the lecture you have seen that if they are anti-parallel spin or parallel spin, the Coulomb integral always survive. Now the exchange integral, so the exchange integral sometimes survive the spin integration, needs the spin orbital I and j to have the same spin. That means that for the exchange integral to survive, they must have the same spin. That is the parallel spin that is being
mm,
discussed. Right. Now back to your Hartree-Fock energy for the helium. So we had this term, this 1 and 1 bar, that is this is alpha and beta. Now as these are your opposite spin, that's why this goes to 0, and only the your Coulomb integral survives. So this is your final result. Now can we simplify this result even more? So yes, let's see what actually. So that is actually your restricted Hartree-Fock. So this is the helium atom. So here is what is actually doing is that this is the first electron, and this is the first electron, and this is the second electron. And here we are saying that the special part to this first electron and the second electron is same. That means we are actually dealing with the restricted Hartree-Fock. Okay, so we can write it as phi 1r, phi 1r. The special part is the same. So therefore, after spin integration, special integral in terms of this orbital must be same, right? So what does they mean actually is that because of their special integral is same, this term and this term become the same. So actually you can write this O1 H1 and 1 bar H1 as the same. So that's what they meant as the generalization. And again, the same similar thing for the special integrals also. If spin orbitals come in alpha beta pairs with the same special part phi, then after spin integration, we can remove the overbar levels. That means the beta levels that they are mentioning on the special orbital integrals. Right? So let's go by one. So I should discuss this. So this is 1 1 bar and 1 1. So this is chi 1 bar, chi1, and here you have 1 1, so that's why chi1 chi1. Now this bar means they are beta spin, and they have separated out here, and this is your chi1, that means they are alpha spin. They have separated out, but as they have the same special part, that's why this is phi 1 phi 1 phi 1 phi 1. That's why you are getting 1 1 1 1. So that's why they have mentioned here. Now for the helium atom, we had these, right? Now we have shown that these two are same, so that's why they have written two times here, and this the bar they have removed. So now they have the integrals in terms of the spatial
So
integral.
the first bracket here means it is Koopman's notation.
Yes,
Yeah.
in generally the Koopman's notation, they use that in the bracket notation, but I don't know why they have used the third bracket here. Maybe this is to denote that you are in the spin orbital case, because see that when you go from this spin orbital case to the spatial orbital, they are using this the first bracket notation, but here they are using the third bracket notation. I think this is because of the spin orbital, but it is nowhere mentioned in his slides that why he has used it. But the idea is clear, right? Now, the restricted
Yeah.
Hartree-Fock, this is called the RHF basically. So, what restricted Hartree-Fock is basically whatever Professor Pal has mentioned for the closed shell system. So, there you spin orbital always come in alpha beta pairs. So, for one special part, you have two spin parts. That is actually basically uh, the restricted Hartree-Fock. This is how
So
we know.
basically, both only the closed shell case is called the restricted Hartree-Fock.
Yes or no, because you can treat the, let's say you have an open chain molecule, sorry,
Hmm.
you have a closed chain molecule, so
Hmm.
you can treat that, so the alpha spin part, so there is, so let's say there are alpha spin and beta spin for each pair,
Hmm.
right?
Hmm.
You can like take the decision to study the alpha part separately and beta parts separately. You don't assume that the alpha spin and beta spin they have the same spatial part. You treat the alpha part totally separately and beta part totally separately. That is actually your unrestricted Hartree-Fock. That is not being discussed here, and that is actually very complex. But there is another part that is called restricted open shell Hartree-Fock, like RHF, UHF, and ROHF. But for this course, RHF is totally fine, but you can treat the closed shell molecule as a unrestricted Hartree-Fock. That is allowed. But for open shell molecule, like when
Can
there is a,
you once repeat like what is unrestricted Hartree-Fock?
so in unrestricted Hartree-Fock, what you do is that you don't assume that the uh, so let's say you have two electron.
The spin or spatial orbitals are same or?
So let's say you have a helium atom, right? So now you have this one special orbital, and you are filling this two electron here. So now
Hmm.
what you are assuming is that the for one electron, that is 1s alpha and 1s beta. So you are assuming that my special part is same here for this alpha beta pairs of electron. That is called the restricted Hartree-Fock. But in case of unrestricted Hartree-Fock, what is done basically, you don't know. So you have a alpha spin and beta spin, that is sure, that is alpha spin and beta spin, but you don't know that this is 1s alpha or that is 1s dash beta. But that means you separately done the Hartree-Fock for this and Hartree-Fock for this, so you don't know that whether this spatial part are same or not. Actually, for the open shell system, it is being seen that the spatial part are not same. They have slightly difference in energy. So actually they are not the same. But for closed shell system, the restricted Hartree-Fock is well enough. We should not go into this discussion because the unrestricted Hartree-Fock and the restricted open shell Hartree-Fock, though their philosophy is same, but the discussion will take, let's say, one or two class itself to show you that how it's done actually. But yes, I'm just mentioning that yes, there are possibilities, the unrestricted Hartree-Fock and restricted open shell Hartree-Fock to treat the open shell type of molecules where you are left with, so your spin, the total spin, the 2s plus 1 is not singlet. It can be multiplet, doublet, triplet like this. So so this is, see that this is the unrestricted orbitals or unrestricted Hartree-Fock. So when all, not all electrons are paired or open shell system, so if we unrestricted the orbitals, allow the spatial part to be different for the alpha spin than the beta spin. So here what they have mentioned is that the chi n bar, so see this is phi n bar and phi n. So they haven't mentioned that this phi n, so they haven't mentioned that this is phi n. They have mentioned this is phi n, and they have said that this phi n bar might be different from the phi n. So introduces spin contamination on all that. So I'll not discuss. Can be easier to converge. Yes. Now there is a pseudo classical interpretation of Hartree-Fock energies. Let's this is also done. So each electron contributes a term, this hij. This basically means your electron is uh, so hij. So this term, this means that the electron in ith orbital has the kinetic energy and the summation of kinetic energy and the nuclear interaction repulsion, and this is the one to one ij, the exchange term and the Coulomb term. Now this is, I think, again discussed in the class also.
Yeah,
Mm,
yeah.
yes. So this is H11, H11 bar for this
Uh,
electron and this electron. This is H2 for this electron, and all that there is one, two, three
uh,
pairs of
just
electron.
to confirm one doubt, like those
Hmm.
J12, uh, like J21 and J12, like if you even if you flip the indices, the terms should remain same, right? Like J12
J,
should be equal to J21.
so so you mean that
That's why we
J?
get two J21, right? Or
Yes, yes. Actually, so you mean the J12 and J, uh, so J21 and J12. So what is that means actually?
because they commute or something.
Not commute. This is because of the your indistinguishability nature. So J21 you can write it as. mm
Is it symmetry
so what you actually writing here is that, should I write in Dirac notation or Copeland's?
or
What you are
Dirac?
Dirac, right? So let's write in Dirac notation. So let's say you have chi2 and so you have 2 1, right? So you have
Hmm.
chi1 and you have a 1 by r12. I'm not writing that. And you have chi2, chi1. Yes. So this is your 1 level and this is your 2 level. This is 1 electron and this is 2 electron. And this is, that means, so I'll not write here, or I can write this term as, I can flip the indexes, right? Because
Yeah.
I can write chi2 2, chi1 1, chi2 2, chi1 1. So this is not the way actually we write the Dirac notation. We write the first electron, second, first and second. So this is, I'm just showing you. So actually this is your chi1 1, chi2 2, chi1
Or
1,
yeah, I can say
chi2.
like J21 is the Coulombic interaction between electron sitting in 1 to 2, and
Yes,
J12 is the
yes, yes. Physically, that's why they should come out to be same. That is your J12, right? Yes, you actually got it right because um, the electrons are sitting in one and second orbital, so it doesn't make any sense to label them as J12 and J21. They has to be same. Okay. So now then again, that Ohm's rule was discussed, that why.
one doubt. Can you go to the previous page?
Hmm,
Yeah, fine. Sorry. Yeah.
okay. So now again the Ohm's rule was discussed. Why? Because So why the high spin state is favorable than your low spin state, right? So now because of this exchange term, because now the condition is
Yeah.
that the gap between the two orbitals is that has to be, so here they have considered the degenerate orbital. This is not always true. It should be emphasized, and which is being emphasized in the class itself, but it is not emphasized here. But thing is that now if you have two orbital which is well separated here, and you want this or this, actually you can say from this discussion, key, because of the exchange term here, I think it will be stabilized, but you are paying more money on this to put this electron on the higher lying orbital, so actually the energy will be higher here. So then the lower or the lower energetics will be for this configuration. So this is only valid when the energy gap between two orbitals that you are discussing with is low or very near degenerate. Now, this is the Hartree-Fock equation. This is F chi1 chi is equal to EI chi I, and this is a very complete uh, integral differential equation. I don't know what that does mean. I think they wanted to mean is that this F depends on this chi I, and to form this air you need this chi, right? So it's a kind of a self-consistent thing, and so that's why they have mentioned that it's a very difficult thing. And then Ruthan, I think this is already touched upon in this lecture, that you introduce a basis. So here actually you are switching from you are actually introducing a basis that is your chi mu bar, and you represent this Fock in that basis, and that gave you this Fock matrix element and this coefficient, and actually this is the heart of your Hartree-Fock equation. And
Can you tell like why this FC equal to SC is not an eigenvalue equation? In the class it was said it was pseudo eigenvalue equation.
yes, yes, because so if you remember in the previous class, I discussed if your OU is equal to U omega, then it's eigenvalue equation.
Yeah.
But here is that, let's say you have a water molecule, right? Water molecule. Now, so the
Okay.
basis you have taken, they are atom centered basis or Gaussian basis, actually what is usually done. So you have taken these atom centered basis, these atom centered basis, and these atom centered basis, and then you form the molecular orbital. This chi is now your molecular orbital, and which is
Hmm.
a linear combination of all the atomic orbitals. Now, the quantum mechanics postulate says that if your Hamiltonian, or if your operator, again I'm telling this, if your operator is Hermitian, then the eigenvectors are orthonormal. But the one electron wave function that you have taken, they are actually coming from solving the different nucleus.
Hmm.
So they are not coming from the same nucleus Hamiltonian. So you cannot say that they are orthogonal to each other. So that's why this
Yeah.
S mu nu was basically
Yeah,
your,
that I got, but like why this is not eigenvalue equation because it does not is not of the form OU equal to E omega.
yes. So actually this S is, so this is mu and this is nu. And
Hmm.
if this is what delta mu nu, then it's a it's a identity matrix. Then your FC is equal to C. Now this is your eigenvalue equation. But as this S is not an identity, because this is not in general, it's not a identity matrix. That's why it is not eigenvalue equation. So if you see the previous lecture, then I think it will be clear, because this S is not an identity matrix or Kronecker delta.
Oh, okay.
So again, the self-consistency thing is discussed here, and this is a pseudo eigenvalue equation. The same thing,
So why is it called then a pseudo eigenvalue?
because later on you have changed the basis to a different basis, and you have solved the eigenvalue equation there. So So in that sense, you can actually change the basis to make this as FC dash is equal to C dash E. So you can change the basis to make it an eigenvalue equation.
Okay.
Now this is a procedure to specify the molecule in the Born-Oppenheimer approximation from the overlap matrix, guess the initial matrix. So there are various initial things that you can done. Then you form the Fock matrix, you solve the FC is equal to SC, and you form the from the MO coefficient, you fall the from the new Fock, and again you check the convergence. I think this is also being discussed. Now, okay, I should the computational cost. I think this is a this thing, this point I wanted to mention that the rate determining step normally computation of O n to the power 4 integrals. So that means let's say your atomic basis is 10, right? So the number of atomic basis or this mu function, let's say you have 10. Now you have wanted now you want to solve this equation, so larger the basis set larger, so that is good actually. So now let's say you want to work with a basis which has a dimension 20, so this is a 2 time increase, right? So you might wonder that okay, so maybe then my cost will be doubles, like doubling the cost, but actually not this. So for this 10 you have a 10 to the power 4. Now you have a 20 to the power 4. It's not a doubling of this. So this 10 to the power 4 and this 20 to the power 4, it's not actually a linear scaling. So if you double the basis, your cost is not going to be doubled. It's actually n to the power 4. That's what it means. So now why this is n to the power 4? So you check this to calculate each mu new element. To calculate each mu new element, what you have to do, you have to sum over this lambda and this sigma. So that is n to the power 2, and for each mu new, that is n to the power 2, and that's give you n to the power 4 scaling. So when MP2 will be discussed, you will see it is a n to the power 5. When CCSD will be discussed, then you will see this n to the power 6. So now there are various techniques by which you can reduce to n to the power 2 scaling. There are multiple things that is advanced thing. Then there is density fitting, Cholesky decomposition, or other thing by which you can neglect this or approximate this 4-index integral by 3-index integrals. So now we get actually the electronic energy or the orbital energies. We got the electronic wave function by which we can get the polarizability and the orbital energy. Okay, so now the orbital energies, so I'll discuss in more detail in the next class, from which you can actually, this gives you the negative of the energy required to remove an electron. That is actually the Koopman's theorem. Okay, and the unoccupied orbital is that very approximately gives the energy required to put an electron in that orbital. That is the Koopman's approximation to the electron affinity. And again, I think it is being shown that the orbital energies, if you sum the orbital energy, it's not the Hartree-Fock energy. Okay, the energy units in the Hartree-Fock is
Uh,
in the Hartree. Yes.
th- there was I had a doubt in one of the question assignment,
Mhm.
like regarding the symmetry in the two electron integral in the of the Ruthan equation.
Hmm.
So there are like symmetry. I mean the mu
Mhm.
si, lambda sigma. If you
This one.
yeah yeah
This is
or sigma lambda. Yeah.
this is antisymmetrized integral or only one the exchange only the Coulomb integral or sigma lambda. Okay.
So this is antisymmetrized, I think.
Okay.
but they write it together using the permutation operator.
Okay.
The entire.
Hmm.
So it was said in the class like symmetry can be because of two things. One is commutativity if between all if the all the orbitals are real, and second is uh, shifting the dummy indices
Hmm.
left.
Hmm.
So can you distinguish the two like between, I'm getting confused.
Okay. Okay. So let's say you have mu and sigma lambda, right?
Uh,
Okay. So the first thing first, this is your one, this is two, this is one, this is two, right?
mm.
So you can do this. Uh,
If
First
they are
thing is that,
real, we can, yeah.
yes, if they are real, you can actually switch this sigma and mu, right? Because
Mm.
in the integral you have mu star 1 and sigma 1. So why, if this is real, that means my sigma star is sigma, mu star is sigma. So I can anyway write that as sigma 1 and sigma star 1 and mu 1. So you can actually get sigma mu mu lambda. So I have switched the mu and sigma here because they are real. I am assuming if they when like they are not real, you cannot do this. Okay. So by the same way, you can switch the other two. So there will be another. There will be another. So there will be four integrals.
Mm.
So actually, what do I mean? You have switched this mu. You can switch this nu lambda. Okay, then again within these two you can switch or what is basically actually um, you can switch these indices as mu nu, or you can say nu
If they
mu.
are not real, then
If they are not real, then you cannot switch this. Actually you cannot switch the real thing to the complex plane, but you can always do the one to symmetry.
okay.
Okay, so then now you have this lambda sigma, and the similar there will be four terms.
Okay.
So that gives you eightfold symmetry.
So each term, like you have written here,
Mhm.
sigma, mu, lambda. So each of these four terms can be written in two ways. Is it? Am I right? Because of
Uh,
because
I'm not sure about this permutation and commutation. What I understand is that if your orbit, so it will be very clear for you. You just write this as in this integration form. Then you can write
okay,
everything very clear. So now you have
okay,
one by one. So whatever the term is there, I'm not writing it here. So then you have lambda 1 and lambda 2. So I have to get this in like integral. So I can switch this one and this one, or I can switch this one and this one. Okay.
oh,
So the integration has to be over. So you can also write uh, this mu star 1 or 1 by R1 2, or let's say here you have this lambda 1. So you can change this 1 and 2 here also. So if you write in this form, that the explicit integration form, then actually you can easily see this eightfold symmetry.
okay.
Okay.
So and also like, can you
Hmm.
like related to the lecture, can you bring some other questions in the assignments from the next?
Yes, so actually, is that if I um, the problem given in the exercise, that is I think very pretty simple, the assignments. So
Yeah,
in the next class,
some
when
are
I'll dis
tricky, but most of them are
yes, some are
simple.
tricky. Most of them are simple. So in the next class, what I'll try to is that. Okay, so if you are interested in the assignment problems, I will try to bring more questions. But what I was thinking is that my logic was is that whatever is not discussed or but required in the uh, discussion, which is explicit or implicitly assume that you can know these things. Those are the things that I tried to cover. So my goal would be in the next classes to discuss the Koopman's theorem and the slides by or the notes by Professor Sale because they are very good. And I'll try to bring more question if I can. And in the later course, what I planned, and you also told, we can do a Python code version of the Hetrifog. And okay, let's see how it goes. Okay, so these are the example of Hartree-Fock energy. So this is taken from McIrey. The only thing is that if this is your experiment, I think that this is the lower bound. You can see that. So the orbital energy that is in negative, right? So they actually come in negative, but so negative energy has no meaning, but they actually get the positive energy. So that's what you have written. So the only thing is that Hartree-Fock is a variational thing, right? You should not get energy that is lower than the actual one. So if this is the thing, so you can see that this is also always in the upper bound. So if this is your actual thing, you always lie in somewhere here or exactly here. So that is true for the 1s, 2s, and 2p. And if you want, I can also show some software programs like Orca, where I can show some typical Hartree-Fock calculation, and I can show you what are the output files means. That I can also show you. So then this is the practical considerations where Hartree-Fock self-consistent usually converges fairly with a good initial case, but there are some problems. There are many things. Uh, like user is responsible for making sure the orbital occupations are reasonable and spin state is correct because O2 is triplet, it's not singlet, so it should not converge to the triplet state. And these are very advanced techniques, direct DIIS and other things. So in PySCF, actually, they use this superposition of atomic density and all this, but I should not go into this. Yes. So these are the things. So the only thing I wanted to mention is that to show you a real data here and what we can calculate from the wave function and the computational cost that why it is n to the power 4 and because that will be necessary in molar cluster theory and couple cluster where you will um, see the scaling. So that was it. And in the next class, we'll try to touch this Koopman's theory and other things. Okay.
Yeah, thank you.